Hello everyone. In this lecture, I am going to explain what is a timing diagram. That is how to draw the timing diagram for combination circuits with propagation delay and without propagation delay, as well as how to remove the hazards from the combination circuits. These two things we are going to discuss in this lecture. Okay. So the topics to be covered here is the timing diagram. The first one is with propagation delay and another one is the without propagation delay. Then we are going to discuss what do you mean by hazards and how the different types of hazards, static and dynamic hazards. Then how to remove this static hazard and dynamic hazard from the combination circuits. Okay, we'll see one by one. So first timing diagram. So it's a graphical representation of input and output signals as functions of time. Yes. So we are going to represent in the XY direction. That is, we know that in digital we are dealing with only binaries, that is zeros and ones only will be there, and we know how to represent 0 and 1s. That is 0 is represented as a low level signal and 1 is represented as a high level signal. So the entire timing diagram should consist of only this low and high level signals. So when you are going to combine this low level signal and high level signal, this looks like a square pulses. Okay. So since take the values of zeros or ones, the graphical a series of square pulses with a variety of time lengths. As this is the time length, so this time length will vary depends upon the delay. Okay. The input and outputs are drawn on the same diagram to show the input and output behavior of the digital system. Yes, the same diagram. That is, first input as we are going to draw, then second output will also draw. So while drawing like this, we can understand the behavior of given combinational circuits, how it is behaving. Okay, due to some time difference. Right. It's usually generated by an oscilloscope or logic analyzer. Yes, actually these square pulses will be generated by the oscilloscopes or logic analyzer. But in digital, we are going to use some simulation tool to generate these signals, software simulator that generate the timing diagrams. A timing diagram shows all possible input and output patterns, not necessarily in order, similar to the truth table. And have a look at this. This is an example of AND gate, and you guys are familiar with this AND gate. See, this is an AND gate symbol, so which is required two inputs X and Y and one output, and this is going to perform the multiplication operation. So the expression is F is equal to X dot Y. Okay, and this is the truth table of AND gate. When both inputs are 0 0, output is 0. When 0 1, output is 0. 1 0, output is 0. When both inputs are 1 1, output is 1. Now for this truth table only, we are going to draw the timing diagram. Okay, so have a look at this. This is the timing diagram of AND gate. So how they are going to draw means, let me draw here. First X signal, then Y signal, then output X. Okay. So let me draw first. Before drawing this, first we need to create some vertical lines. So this vertical line indicates the time interval. See, like this, you can draw this vertical lines. This is time t1, t2, t3, t4, t5. So first condition is x is 0, y is 0. So I'm going to draw x is 0 and then I'm going to draw y is 0. So this is low level signal, this is 0 0. So what will be the output f? So output f is also 0. Okay. Then I'm going to change y value is equal to 1 and x value is equal to 0. The same second condition. So x value is 0 means again it is going to continue the same level, and y value is 1 means the level now changed into 1. Now at this time, what is the output? So 0 1, again the output is 0 1. Okay, right. So two conditions are over. The third condition is 1 0. So x is now changed into 1 and y is now changed into 0. So this is 1 and this is 0. Now for this condition also output is 0. Okay. So finally I'm going to change this x is equal to 1 and y is equal to 1, and now f value will be changed into 1. Okay, so this is what the timing diagram representations of AND gate. Here there is no delay is used. So whenever this x and y is changing, outputs are changing. Okay, there is no delay here. So this is a without propagation delay example. I hope you guys understand. So first draw these vertical lines T1, T2, T3, T4, T5. Then draw your inputs X and Y with the different combinations from the truth table. Okay, right. And see, this is another one example for without propagation delay. And this is a NAND gate timing diagram. So what is NAND gate truth table? A, B, and output is Y. That is, NAND gate is quite opposite to AND gate. So these three outputs are 1 except this one. So first A, B are 0, 0. See, A is 0 and B is 0 and Y is 1. Okay, then 0, second condition 0, 1 condition. So this is 0, 1 and output is 1. And third condition 1, 0, 1 and 0, output is 1. And fourth condition 1, 1, output is 0. So the level is very, very important. 0 means we need to represent in the low level signal, and when it is 1 we need to change the level is into 1. That is very, very important. Okay, so this is one of the examples for without propagation delay. Now with propagation delay, have a look at this. This is an example of a NOT gate. So NOT gate, only one input is needed and one output will come. So we know that the NOT gate truth table is input, this is input and this is output. When I'm going to give 0, here output 1 will come. When I'm going to give 1, here output 0 will come. This is the truth table of NOT gate. Have a look at this. Up to this point, x value is 0. So up to this point, x value is equal to 1. But actually, the output will change here, but due to some delay, see, due to some delay in the input, sorry, not an input, due to some delay in the NOT gate, that is here the delay is, first delay is, it is epsilon 1, so that delay is, maybe it is in a 5 nanoseconds, just imagine 5 nanoseconds, so this time period is the 5 nanoseconds time period. So when I am applying x is equal to 0, the output is equal to 1, but it will stay after 5 nanoseconds because it takes 5 nanoseconds to produce the outputs. Okay, so then I'm going to change my input is displays. See, my input is equal to 1 now. So due to this 5 nanoseconds delay, the output it won't change at this point. Okay, so after 5 nanoseconds delay only, the output is changing. This is 1 means this is 0. Okay, so this 5 nanosecond is the delay of this NOT gate. Okay, whenever the device is having some delay, the output will be delayed. It depends upon the timing of the particular gates. So here NOT gate is having 5 nanoseconds time delay. So when I am changing my input is 0 to 1, my outputs are changing from 1 to 0, but it will take a 5 nanosecond to change the second combination output. Okay, and I can see I can change my input is into 0, but at this moment the output need to change, but it will take some time delay because while I am applying this 1, it took a 5 nanoseconds delay, then I am going to change it to 0, again it will take another 5 nanoseconds delay to change the output. So this is what propagation delay in time representation. Okay, I hope you guys understand. The previous, see, in AND gate, when I am changing this 0, at that moment itself output is changed. See, when I am changing into 1, so at that moment itself output is changed. See, here, when I am changing here 0 to 1, same time it is changing. So, the meaning is, here there is no delay. But here there has been a delay, that's why it will take some time period to change the output. This is one example for delay, propagation delay. And have a look at this. This is another one example. Two gates are involved. This is AND gate. This is a NOR gate. So two inputs here A and here B is equal to 1, and this is gate G1 and gate G2, and here C is equal to 0. Okay. So B is equal to 1. When I'm going to give A is equal to 1, my G1 value is equal to 1. Okay. So say take a look. Have a look at this. A value is equal to 1, I am going to change from here. At this point, I am going to change A value is equal to 1. So already B is equal to 1, now A is equal to 1, so G value is equal to 1. But this G1 is having some 20 nanoseconds time delay. which means the G1 will produce the result after 20 nanoseconds delay of the A is changed. So see, this is the 20 nanoseconds time delay. So the A value 1 still continues up to this place. So after this place it is changed into 0. So now this is A is changed into 0 means this G1 value is equal to 0. But at this moment it will not change because this G1 is having 20 nanoseconds time delay. So after this 20 nanosecond from this point, then only it is going to change into 0. Okay, right. So this G1 is having 20 nanoseconds delay. Then another one gate is there. So here one input is applied 0. Okay. So this gate is also is going to produce the result with the 20 nanoseconds delay. Because here already it is delayed by 20 nanoseconds. Here there is no delay. Delay is equal to 0 seconds. But due to this G1, it is also going to produce with 20 nanoseconds delay. Have a look at this. So G1 is changed here. Okay. But G1 value is what? 1 and this is 0. According to the NOR gate, this value should be 0. So when it is changing into 0, see, after 20 nanosecond time delay only, it is changed into 0. Okay, then I'm going to change A1 value is equal to 0 here. Okay, again this G2 will change after 20 nanoseconds delay. If one of the device will create some propagation delay, it will affect the rest of the circuits. Okay, this is another one example for propagation. Next, one more example. So one input X, other input is Y. So here X is applied at the 0th second and Y is going to apply it after 1 microseconds only. So what will be the output of this AND gate? Let's have a look at this. So X value, Y value and Z value, and this vertical, the dash lines are time period. So I'm going to give my X1, X value is equal to 1 at this point. See, it is a high level, so here the value is 1. So now I have applied X. When I'm going to apply X, after 1 microsecond time delay only the Y value will be applied. See, this is a 1 microsecond time delay. Then I'm going to apply Y value. Okay, now this is AND gate. Now both are 1, 1, so Z should be 1. But Z output also will come after this 1 microseconds delay only. See, this is 1 and this is also changed into 1. So at this moment the output should be high because both are 1, 1 AND gate, it should be 1. But here some time delay is there. So this delay is due to this. So not due to this 1 microsecond. So this delay is due to this AND gate. So here AND gate is having some 1 microseconds delay. Okay, similarly see here, this is 0. So this is 0 and this is 0, so output is also 0. So again I'm going to change my input is from 0 to 1. So this is 1. See, here I'm changing my input. Okay, as well as after 1 microseconds my Y input is also going to be changed 1 here. So again my circuits need to produce the outputs here, but it taken us some time delay due to this AND gate propagation. Okay, so I hope you guys are understand what we mean by propagation delay, with propagation delay and without propagation delay. Okay, right. The next thing is hazards. So hazards, if exist in digital circuit, causes a temporary fluctuation in the output of the circuits. We know that in digital circuits only zeros and ones only used. Say for example, for AND gate I am giving 1 1 is equal to 1. If suppose this 1 is not coming, here the output is 0 is coming, means here there will be a problem in this gate. So that is what it is hazard. Then what type of hazards, that we need to identify with the help of some logics will be there, that we are going to discuss now. Okay, so the temporary fluctuation, they are expecting one output but unexpected outputs are coming, means that is called as hazard. Okay, so in other words, hazards in a digital circuit is a temporary disturbance in ideal operation of the circuit which is given sometime get resolved itself. Right. So these disturbances or fluctuations occur when different parts from the input to output have different delays, and due to this fact, changes in the input variables do not change the output instantly, but do appear at the output after a small delay caused by the circuit building elements or the gates. Okay, so hazards means it is in a fluctuation, that is unwanted output. Okay, so how to avoid these hazards means either we need to increase the propagation delay in the path seen, that is so here this is the output and these are all the input. Okay, so if here 0 seconds, here 0 seconds will be there means then this output will comes in the perfect time. If suppose here the time delay is 5 seconds, time delay is there, then this output will also produce in after 5 seconds only. If suppose you are in need of the output in the 0th time second, means what you need to do? Either you need to increase the time delay of this first AND gate, otherwise you need to reduce the time delay of this. So in this way only we can be able to eliminate this hazard from the combinational circuits or digital circuits. Okay, right. Let's see. There are two types will be there. One is a static hazard, another one is a dynamic hazard. So what do you mean by static and what do you mean by dynamic? So in digitals, we know that ones and zeros only we are using. Okay, we are expecting the output is 1, but the outputs are coming 0. We are expecting the output is 0, but the outputs are coming 1. So this is called as static. Only one output is coming. Okay, that is just now I told you know, for AND gauge, 1 1 I am giving, here my output is 1. If suppose here 0 is coming means there will be a fault is there, that is what a hazard. So this is hazard is called as static hazard because only one output is coming. The same concept here. For dynamic hazard, the same AND gate you can take. So 1 1. First it is producing the output as 0. Second it is producing the output as 1. Third it is producing the output as 0. So and fourth producing output is 1. Okay, expected output is 1, but before producing this 1, it is producing some 3 different outputs. So which means the outputs are changing dynamically. So that's why it is called as dynamic hazards. Okay, more than once the outputs are changing before producing the original result. That is called as dynamic hazards. We'll see one by one. So have a look at this static hazard. This is a static 1 hazard. This is static 0 hazards, which means static 1 hazard means we are expecting output. That is, expected output is 1, but we are getting the output is 0. That is what it is, static 1 hazard. And here static 0 hazard is there. We are expected the output is 0, but the output says 1 is coming. So this is the static 0 hazard. So we are expecting 0, but 1 is coming. So it is static 0 hazard. Okay. Takes place when change in an input causes the output to change momentarily before stabilizing to its correct value. Yes. Based on what is correct value, there are two types of static hazards shown in the below image. That is a static 1 hazard and static 0 hazard. So static 1, we are expecting the output is 1, but 0 is coming. That's why static 1. Let us see in AND gauge 1 1, the expected output is 1, but it is 0 is coming means. So this hazard is called as static 1 hazard. If suppose for OR gauge I am giving here 0 0 means actual output is 0 but 1 is coming means, so this static 0 hazard. Okay, what we are expecting, that is what we are hazard. Fine? Right. Then how to detect the static hazards using K-map? See, write down the output of the digital circuit. First they will give the circuit. Okay. So they are going to give one circuit. In that circuit, identify is there any hazards and how to eliminate the hazards. That will be your question. So first we need to write the expression from the circuit. Let us see. This is AND gate and this is AND gate. This is OR gate. So here two inputs are coming. That is A, B, C, D means. So first we need to write the expression for this circuit. So that is Y is equal to, here the output is AB and here the output is CD. So Y is equal to AB plus CD. This is your first step. Second step, draw the K-map for the function. So for this expression we are going to draw the K-map. Just reverse process. So far we have been discussed the combinational design procedures from description to truth table to KMAP, and KMAP to logical diagram. But for this hazard detection, we are coming from logical diagram, then expression, then KMAP. Okay. So if there is exists any pair of cells with the ones which do not appear to be in the same group, it indicates the presence of static one hazard. Each such pair is a static one hazard. Let me explain with an example. So have a look at this example, and look at the diagram of this one. So P, R, Q, three input is there, and one NOT gate, here one AND gate, here one AND gate, and one OR gate is there. Okay. So first write down the expression for this circuit. So the expression is, this is a R bar. So here P is coming. So this is a PR bar, and Q, and this is OR, so this is QR, and this is OR gate, so the expression is PR bar plus QR. Okay, so for this we need to draw the K map. So here totally how many variables are used? P, R, Q, three variables are used, so we are going to use three variable K map, so PQR is given. Okay, so for getting this PR bar, where I need to mark the ones. Okay, see. Let me draw the given map. This is P, Q, R, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So now I am in need of a P, R bar. So P means definitely this value should be 1. So definitely the answers are in these four boxes 1. Okay, so now I am in need of a R bar. So R bar I am in need means, so see where R bar is there, 0, 0. Wherever R is having 0, we need to consider that part. So this is 0, 0, and here R is 1, here R is 1. So these two boxes it won't come. So this box will come, and the last box it is 1, 0 is there. So this box will come. This is for PR expression. Okay, so we can make these two are one pair. Now write the expression for this. So left side P is there, so P, and the top side 0, 0, and 1, 0 is there. So Q get cancelled, and this is R bar. So these two places we need to fill. Similarly QR. So for QR, QR is in the top side. So where QR, these places the QR. So P won't come, so definitely we need to fill here. So these two are for QR. Okay. Now let me explain what is hazard here. So let us take P value is 1, R value is 0, and Q value is 1. So what is the output of for these combinations 1, 0, 1? So 0 means this is 1 up. So this is 1 now, and this is 1 now. So 1, 1, here the value is 1, and here also this is 0. So 1, 0, this is 0. So now this is 1, this is 0, the output is 1. The expected output is 1. But, so due to this NOT gate, here some 5 nanoseconds delay is there compared with these 3 gates. This one, this one, this one. For these 3 gates there is no delay, but here there will be a delay. Okay, so what will happen when I am applying this 101? Here some delay is there. Okay, so delay is there means, so here this one it won't reach this AND gate first. Okay, so which means here 0 will be there. So 0 means here also 0 will come, here also 0 will come, and the final output here 0 will come. Actual output is 1. But we are getting the output is equal to 0, which means here static 1 hazard is there in this circuit. Okay, so how to avoid this hazard means, see already we are having one group, so this is a one pair and this is another one pair. Now our ultimate aim is to reduce this nanoseconds delay, otherwise we need to increase the components. So for increasing the component, what I am going to do means, see, I am going to make these two are one pair. So if I am making these two are one pair, means what will happen? One extra component will be increases, that is P and Q will be increases. It will come. Okay. So have a look at the next one. So when I am using this pair, PQ is coming extra. So see, I have drawn PQ is extra. So now the same concept 1, 0, 1. Now see here, actually our expected output is 1 now. Okay, so now don't bother about this NOT gate, whatever it is having the delay. So this is 1 now. So whatever may be the output here 0 or 1, here 0 or 1. Have a look at this of AND gate. So here 1 is coming and here 1 is coming. So this is 1. In OR gate, any one of the input is 1. Here automatically the output 1 will come. So here this NOT gate is having delay or it is not having delay. Nothing to worry. So with the help of this added not AND gate, it will produce the result very quick manner because here this AND gate number 1, 2, 3 are nothing having any delay. So we are getting the output in a fraction of time. Hence the hazard is solved. That is the static hazard is solved. So there are two ways. One is reduce or increase the delay, and second one is add extra components. These are the two methods to reduce this hazards. So this is the example for static hazard. So I hope you guys understand. Next we'll move for dynamic hazard. So first dynamic hazard, as already I have explained more. It is AND gate 1 1, output should be 1. So before getting this 1, the outputs are automatically changed into 0 1 0. Finally it is producing the output is equal to 1. So see, for a single NOT gate we are getting 4 outputs. So this is what dynamic hazard. So some introduction part is given here. Okay, so let's directly go to the problem. So see, this is one circuit is given. So initially here the values are taken 0 0 0. So this is 0, this is 0. So 0 0 means here NOT gate, this one NOT gate, sorry OR gate. So 0 0 in OR gate, 0 will come, and here 0 will come, and NOT gate, so 0, the complement is 1. So here 1 will come, and this is 0. So 1 0 here in NOT gate, 1 will come. Okay. Similarly, this one will comes here, and here 0 will come. So 0, this is changed into 1. Here 1 will come. So this is 0, this is 1. So here 0. This 1 will comes here. Yes. The output is 1 for this input. When A, B, C are 0, 0, 0, output Y is equal to 1. This is what our actual output. Okay. So we are going to get the output is equal to 1 only, but due to the delay of this NOT gate, sorry, OR gate, AND gate, we are going to get this output after some 2 to 3 transition. Okay, right, have a look at this. So D1 less than D2 less than D3. So D1 is having lesser delay compared to the D2, and D2 is having lesser delay compared to the D3. So whatever you are changing here, first this D1 will react, second this D2 will react, third this D3 will react. Okay, we'll see one by one. So first I change 0 to 1. B input, I am going to change 0 to 1. So what will happen? This is 0, and first see, as per the concept, D1 is having lesser delay. Okay, so first the changes will be going to be happen through this AND gate only. Okay, so 0. So this is I'm going to change into 1. So this one change it into 0 now. So this 0 will comes here. So 0 1, this AND gate is 0. So already here 1 0 is there. So 0 0. Now the output is 0. Okay, see, the transition is through this way because this D1 is having lesser delay compared to this D2 and D3. This is the first transition. Okay, now D2 is having lesser delay compared to the D3. So first transition is happened through this way. So we are getting 0 here. The next second transition is through this way. So have a look at this 0 and 0 1. So now this is 1, this is 0. So 0 1 in OR gate. Previously it is 0, now it is changed into 1. So here 1 will come, here 1 will come. So 1 1. Now it is changed into 1. So here 0 is there. So 1 0. Now it is changed into 1. This is the second transition. And finally, D3 is having the highest delay, so the final transition is see through this way. That is, here 1 is changed to 0. So this is 0, this is 0 in OR gate, this is 0. So here 0 will come, already 1 is here, so 0, 1, it is 0. So this is 0, this is 0, so now it is 0. Okay, right. And see, actually we are going to get output is equal to 1 now. When I am going to change here 0 into 1 now, see how many times the outputs are changing. How many times the outputs are changing. For digital circuits, there will be only single outputs. But here 4 times the outputs are changing. So this is what the dynamic hazard. Okay. So for removing this dynamic hazard, what to do means we need to keep the same delay in all these 3 gates. Say for example, as for this example here, it is a 2 nanoseconds delay. Here it is a 4 nanoseconds delay. Here it is 6 nanoseconds. So what we need to do? Either we need to keep all the 3 devices same delay. That is here 4 means here 4, here 4. Otherwise here 6, here 6 and here 6. Otherwise in all the 3, 2, 2, 2. Then only we can be able to avoid this dynamic hazard. So I hope you guys understand how to identify the hazards and how to remove the hazards from the combinational circuits. So let me conclude quickly. So we have been discussed the timing diagram with propagation delay and without propagation delay, and we have seen some examples for propagation delay. And hazards are static and dynamic hazards we have been discussed, and with some examples we have discussed how to remove the hazards from the combinational circuits. So thank you. See you in the next lecture.